In this video, we're going to talk about sketching curves. So this is the end of Unit 3. It's also kind of the conclusion of everything that we've learned so far in this class about derivatives. So we're going to be looking at things like going all the way back to limits, domain and range, what we just learned in lesson 16 with finding maxes and mins and inflection points and all of that good stuff. But the bottom line is, using all of the things that we've learned so far, all of the concepts, we can get some very nice pictures of graphs without a computer or calculator. So by the end of this lesson, you should be able to answer the following little question. How can we figure out what a graph looks like just from the equation and what we know about limits and derivatives? And by the end of Unit 3, we're still in that big question in the second half of Unit 3, what is the point of finding derivatives? So let's do the warm-up real quick. So we want to draw an example of a function that is increasing, concave down, has a horizontal asymptote, and has a vertical asymptote. So I don't need an equation. I just want you to draw a picture to show me that you understand what all of those words mean. So, let's see. Increasing and concave down must look something like this. Okay. We also need something with a vertical asymptote. So maybe we continue that down and make that a vertical asymptote. We also need a horizontal asymptote. So maybe we continue this outward and say that there's a horizontal asymptote right here. All right. And that would be a function that meets all of our criteria. So in the last lesson, we talked about what the first and second derivatives tell us about a function's graph. But like I was saying, together with a bunch of other stuff that we've done, so like limits, some ideas from pre-calculus, that's like domain and range, we can draw really nice graphs of functions without technology. So what I want you to do really quick, so pause the video. I'm going to keep matching the words now, but pause the video, try to match the words yourself, because that's going to be a good review of everything that we've learned so far. And I should mention that this one is all together. So this is one item right here. Okay, so that is what your words should look like matched up. So if you got most of those, great job. That's what we're looking for. The one last thing we're going to talk about with graphing functions is symmetry. So we haven't talked about this yet. And there's a couple of problems on your homework that deal with it. So I want to make sure that we cover it in detail. So a function can be symmetric in three different ways. So the first way is if we have this picture over here where it's like we're folding a piece of paper. So folding paper in half. All right, so you notice in the picture, if we were to fold this graph along the y-axis, it would match up if we folded it in half. This type of function is called an even function. Okay, and algebraically what we're saying is f of negative x is equal to f of x. Okay, and so all that means is these are your negative x values, these are your x values, and you can see from the picture that they're equal. All right, the second type is this second picture over here where it's like we turn the paper upside down and it looks the same. Okay, so this type of function is called an odd function. So just so we're clear, if we were to take the graph and rotate it 180 degrees, so if we literally turned our paper upside down, the graph would look exactly the same. Okay? And algebraically, what we have for this is f of negative x is equal to negative f of x. So over here, we have our negative x's, or how should I say this? We'll write it over here. So this side of the graph is f of negative x. This side of the graph is, how do I want to write that? It's not quite as nice as the even one. We'll say this half of the graph is f of, yeah, that makes sense. Okay, so yeah, we have, yeah, okay, I'll write it just like the even one. So over here, we have our negative x's. Over here, we have our positive x's, and we notice that the things with the positive x are exactly the opposite of the things with the negative x. So that gives us our statement for odd functions. And the last type of symmetry you might see, you've probably seen this one before, you probably just didn't realize it. So this one is if we shift our paper left or right, and we get the same graph. So these types of functions with this symmetry, where like we take the function, we shift it down the page, and it keeps looking the same, we call these periodic functions. And so now you're probably like, oh yeah, trig functions. So I would say the classic examples that you want to look at for these three: an even function. The classic example is x squared. Where do I want to write this? Okay, maybe I'll write it over here. So example, x squared is your very typical even function. X cubed is your typical odd function. And for periodic, pick any of the trig functions. Okay, so those are the pictures you kind of have in your head. But the pictures that we have here on the right are nice too. Okay, so those are our three types of symmetry. So given that, we should now be able to use all of the things we've learned so far. So I'm scrolling up, but don't let this problem scare you. So we should be able to learn all of the things we've learned so far together with symmetry, and we should be able to analyze a function in detail. So for this first example, to save time in these notes, the derivatives will be given to you, okay? And we're going to then work through all of the different aspects of a curve that we've learned about, and at the end we'll finally be able to sketch the graph. So let's start with the domain. So our function, so I'm going to highlight the function because this just gets to be a lot of work. So our function is y is equal to x e of x. So for our domain, what we want to think about is, what are the domains of the individual functions? Well, the domain of x is negative infinity to infinity, as is e to the x, negative infinity to infinity. So the domain of our entire function is just going to be negative infinity to infinity. Next, we want our x-intercepts. So it might be a while since you've solved for an x-intercept. Actually, how about we do our y-intercept first? I think that's easier. So for y-intercept, what we want to do is set x. Oh, wait. Hang on. Yeah, we want to set x equal to 0. Okay, sorry, getting confused here. All right, so we want y is equal to 0 times e to the 0, which is 0. So our y-intercept is 0, 0. Okay, for our x-intercept, we want to set y equal to 0. So we have 0 is equal to x e to the x. And so since this is a product of things, that means either x is equal to 0 or e to the x is equal to 0. But if you know anything about e to the x never equals 0. So this one actually doesn't tell us any x values, and our x-intercept is still only 0, 0. Okay? Next, we're going to talk about symmetry. So we want to test for symmetry algebraically because we don't know what the graph looks like. So I'm going to quickly run through each type of symmetry until we get one that works. Okay? So for even, the definition is we plug in negative x and we get the original function back. So what I'm going to do is I'm going to start with f of negative x is equal to negative x e to the negative x. Well, that is definitely not equal to the function itself. And so actually let me write this a little different. So first we have f of negative x is equal to negative x times e to the negative x. This is not equal to f of x, nor is it equal to negative f of x, because we also have that negative in the exponent of e. Okay, so it's not even, it's not odd. Maybe it's periodic. Let's check. So for that, we would want to plug in f of x plus p, and that's equal to x plus p times e to the x plus p. Well, if I add something to the front, see, here's the problem, is x is not periodic. Nor is e to the x. So this is not going to be equal to f of x. Okay, so it's not periodic, so it must have no symmetry. Okay, next we want horizontal asymptotes. So if you remember from way back at the beginning of this class, we said horizontal asymptotes are when we take the limit as x goes to infinity and negative infinity. So first we're going to do the limit as x goes to infinity of x e to the x. I'm trying to decide whether I want to zoom in or out here. I think zoomed in is a little better, but I want to make sure you can see the function. Okay, so of x e to the x. So this is going to give us infinity times infinity, which is just infinity. If we go to negative infinity, so limit as x goes to negative infinity. Oh, come on, pen. Okay, it's being like that this morning. Sorry. All right, there we go. So limit as x goes to negative infinity of x e to the x is equal to negative infinity times 0. Uh-oh. This means we need L'Hopital's rule. So let's see what we can get here. So we're going to move the e to the x to the bottom. I think that should work. So we're going to get limit as x goes to negative infinity of x over e to the negative x. Yeah, I like that. Okay, now from that we get an infinity over infinity situation. So we can use L'Hopital's rule and we get the limit as x goes to negative infinity of 1 over negative e to the negative x. And now if I plug in negative infinity, that will give me 1 over a really big negative number, because e to the minus infinity is e to the infinity. That's infinity, but we have a negative outside. So 1 over a really big number is just going to give me 0. Okay, so our horizontal asymptote is x is equal to 0 as y equals 0 as x goes to negative infinity. So it's only a one-sided horizontal asymptote. That's pretty important. As far as vertical asymptotes, well, we don't have any, because we don't have a rational function. So we don't have a denominator. okay? So that means we can't have a vertical asymptote. Well, I say no denominator. We also don't have any trig functions running around, so that also means we can't have a vertical asymptote. Okay, so now, finally, it's time to find our critical numbers. So, critical numbers for f prime, we want to take f prime, so that's this over here, and we want to set that equal to 0. So we have 0 is equal to e to the x times x plus 1. So we set each of these factors equal to 0. And we don't get any critical numbers from e to the x because that's never equal to 0. But we do get that x is equal to -1. So our critical number for f prime is -1. And for f double prime, we have e to the x times x plus 2. So let me highlight that real quick. All right, so our critical numbers there, we have 0 is equal to e to the x times x plus 2. So we have 0 is equal to e to the x. Again, no critical numbers from that, but we also have 0 is equal to x plus 2. So x is equal to -2. So our only critical number for f double prime is -2. Okay, so now it's time to go into our sign chart. So f prime, first, let's draw a number line. Let's put our critical number on there, so -1, and yeah, okay, that's fine. All right, so let's write our factors over here. So we have e to the x and x plus 1, and then we're going to end up multiplying these and getting f prime. So e to the x is going to be positive no matter what number we plug in. X plus 1 is going to be negative for anything less than -1, and positive for anything greater than -1. Okay, so we multiply these signs, we get negative on the left, positive on the right. So I know that this is decreasing on the left, increasing on the right, and I know then that -1, so let me maybe do this in red just so that it's clear. We know that -1, if we're going from decreasing to increasing, that's a local min. Okay? Now let's do our sign chart for f double prime. So we have one critical number at -2. We write our factors. We have e to the x, we have x plus 2, and when these multiply, it's going to give us f double prime. So again, e to the x is always positive. X plus 2 is going to be negative to the left of -2 and positive to the right. So we have negative on the left, positive on the right. So our second derivative tells us that we're concave down on the left, concave up on the right, and that means that an inflection point occurs at x is equal to -2. Okay, so that was super quick. We have our sign charts done. So let's see what we can do from here. Okay, we already said a lot of this stuff. So I'm just going to rewrite some intervals really quick. So from our sign chart, we know our interval of increase is -1 to infinity. Our interval of decrease is -infinity to -1. Local max, we have, let's see, it occurs at, oh, we have no local max, my bad. Local min, it occurs at -1, and if we plug in f of -1, that's equal to -1 e to the -1, which is -1 over e. Okay, inflection point, we have it occurring at -2, and then f of -2 is equal to -2 times e to the -2, which is equal to -2 over e squared. And that kind of goes into the concave down. Hang on, let me rewrite this. So negative 2 over e squared. Okay, so that's my inflection point. Concave up, again, comes from our sine chart, so that's negative 2 to infinity. Concave down is negative infinity to negative 2. And finally, we can draw our graph. So let's first put in our asymptotes. So we do have a horizontal asymptote on the left at 0. So the x-axis is going to be our horizontal asymptote on the left side. And I'm only going to draw it on the left because we don't have one on the right, and that's just going to get confusing. Okay, now we probably want to put in our extrema. So we know that a local min is negative 1 comma negative 1 over e. So you're probably like, what is 1 over e? Well, let's see. So we can put it on the y-axis correctly. So let's see, negative 1 divided by e is equal to negative 0.36. So I'll do that in red so that you know it's not part of the answer. Okay, so basically we're going to have a point at negative 1, negative 0.36. Okay, so that's our minimum. We have no local maxes. We do have an inflection point at negative 2 over e squared. So let's see what that is. Negative 2 divided by e squared. Negative 0.27. Okay, these axes kind of suck. Sorry about that. So let's see. Negative 2, negative 0.27. So it's going to be like that. It should look a little higher than the first point that we drew. So let me just make a little note. Okay. Let's see. All right, so now we need to actually draw in what our graph looks like. So this is going to be kind of tricky because our points are close together, but we can do it. All right, so we're concave up from negative 2 to infinity, and we're decreasing. Okay, so let's kind of break this down. So between negative infinity and negative 2, we're decreasing and we're concave down. So that should look something like this. So it's not going to look extremely concave down, but that's just because my points are so close together. Now, between negative 2 and negative 1, we are decreasing and concave up. So that'll look something like this. And then, oh, right, I had another point. I had my intercept at 0, 0. Can't believe we forgot that. Okay, now from negative 1 to infinity, we're increasing and we're concave up. So that's going to look like this. And we didn't have an asymptote on the right side, so my graph looks something like that. Okay, and that's all there is to it. So the reason we have this draft axis here is if you start drawing the graph, that's actually where I would suggest you start drawing the graph. Make sure you can get everything on there and then go and do your final copy that's nice and cleaned up. Okay, so I just drew on the final graph, but that was to save time. All right, so don't want this video to get too long, so let's try and squeeze in one more example before my computer decides to cut off the recording. All right, so our next example, we have y is equal to 2x squared over x squared minus 1. Okay, so let's start with the domain. So domain, here we have a fraction, so we need to figure out where x squared minus 1 is equal to 0. Well, that's going to mean x squared is equal to 1, so x is equal to plus or minus 1. So our domain is going to be negative infinity up to negative 1, union negative 1 to 1, union 1 to infinity. Okay, y-intercept, let's plug in 0 for x. So we have y is equal to 2 times 0 squared over 0 squared minus 1. So that's going to be 0, 0. Sorry, the y-coordinate's equal to 0. X-intercept, let's plug in 0 for y. So that's 2x squared over x squared minus 1. So that means 0 is equal to 2x squared, which means x is equal to 0. So our x-intercept, again, is only 0, 0. Okay, now let's test for symmetry. So let's start by plugging in f of negative x. So that's going to give us 2 times negative x squared over negative x squared minus 1. Now if we simplify this, when we square those negative x's, we're going to get back the original function. So this is actually an even function. Now if our function is even, it cannot also be odd. It could be periodic, but we don't have any trig functions, so it's definitely not going to be periodic. And it can't be neither because we got an even function. Okay, so this is an even function here. So just for completeness, we'll say that that's f of x. All right, so now let's do our horizontal asymptotes. So we have the limit as x approaches, we're going to do both at the same time here because it's a rational function. So as x approaches positive or negative infinity of 2x squared over x squared minus 1. So here we can multiply by 1 over x squared over 1 over x squared. And we get the limit as x goes to plus or minus infinity of 2 over 1 minus 1 over x squared, which gives us 2. So the, or actually let's spell out one more step. 2 over 1 minus 0 is equal to 2. So the horizontal asymptote is going to be y is equal to 2. And that's on both sides. Vertical asymptote, well, we have 2 of them because we already solved for the numbers where the domain does not exist. So negative 1 and 1 not in the domain. So our vertical asymptotes are x is equal to negative 1, x is equal to positive 1. All right, let's find our critical numbers. So that comes from our 2 derivatives over here. So f prime critical numbers, we need the spot where the numerator is equal to 0 and the denominator. Okay, so we haven't really seen a fraction yet, but that's okay. We're going to get it. And I'm going to go ahead and set up the f double prime too, just so I don't have to keep scrolling up the page. So I need where my numerator is 0 and where my denominator is 0. Okay, now we can scroll down a bit. All right, so first of all, I get x is equal to 0 from this first one. I get x squared minus 1 is equal to 0, which gives me x is equal to plus or minus 1 from that second one. Here, I'm going to get 3x squared plus 1 is equal to 0. So x squared is equal to negative 1 over 3. Okay, well that's none because we can't have a square equal a negative number. And then finally over here we have x squared minus 1 is equal to 0. So x is equal to plus or minus 1. Okay, great. So we have our critical numbers. So for f prime, we have negative 1, 0, and 1. F double prime, we have negative 1 and 1. Okay, so let's make our sign charts. So for f prime, I put my 3 critical numbers on there. We have negative 1, 0, and 1, and I write my factors over on the left. So we have negative 4x, and we have x squared minus 1 squared. So anything squared is going to always be positive. So no matter what I plug in, this thing is always going to be positive. Negative 4x is going to be positive for anything less than 0, and negative for anything greater than 0. So if I then multiply these signs, I'm going to get positive, positive, negative, negative. So what this tells me is I have increasing on the left, decreasing on the right. So if we're going from increasing to decreasing, a local max is at x is equal to 0. Okay, let's do our second derivative. So our critical numbers, -1 and 1. Our factors, we have 3x squared plus 1 and x squared minus 1. We have 3 of those. So now it's not always positive, so I'm going to go ahead and write 3 of them. Okay, and then we have f double prime. All right, so 3x squared plus 1. Well, I think that's always going to be positive, because even if we plug in a negative number, we're going to get a positive for x squared, and then we're multiplying that by a positive and adding 1. So that's always going to be positive. X squared minus 1, if we stick in something in between -1 and 1, that's going to give us a really small number. So we're going to get a negative in the middle of those, but we'll get a positive everywhere else. Okay, so then f double prime, we have positive, negative, positive. Okay, now here's where it gets confusing. So the concavity has flip-flopped across -1 and 1, but -1 and 1 are actually not inflection points. And why is that? Well, the function is not continuous at -1 and 1. So here we have concave up, concave down, concave up, but no inflection points because -1 and 1 have vertical asymptotes. Okay, so let's write all of this into our blanks. So intervals of increase, we have -infinity to -1, union -1 to 0. Intervals of decrease, we have 0 to 1, union 1 to infinity. Local maxes, we have at 0, so f of 0, oh boy, what was f? F of 0 is 0. That was our y-intercept. So our local max is 0, 0. Local min, we have no local min. Inflection points, we have no inflection points. Concave up from our sign chart, we have -infinity to -1, union 1 to infinity, and concave down, we have -1 to 1. So I'm sorry I'm rolling kind of fast, but you can always pause the video and think about what I'm saying. All right, so now let's sketch our graph. Like I said, I'm trying to get through this before my computer cuts out. So let's put in our asymptotes. So we had an asymptote at y is equal to 2. That was a horizontal asymptote. So we draw that in. We also had vertical asymptotes at 1 and -1. So we draw those in. So asymptotes are always first. Okay, so we have our asymptotes. Now let's draw our point. We know there's a point at 0, 0, and that's a local max. So that's going to do something like this. And we know that it's, let's see. Now we kind of do our increasing, decreasing thing. So increasing, -infinity to -1, and it's also concave up. So increasing, concave up from -infinity to -1. Then from -1 to 1, we have concave down. And decreasing from